All right, week 109. What's up, everyone? Welcome to week 109 of building my own operating system. Let me just quickly get set up, send a ping out to the Discord. Yeah, so this week we are working on more of this threading and scheduling and stuff like that. Context switches. All right. And I'm pretty excited about it. Last week we made some good progress. Let me just quickly show what we got going on. This is the state of the kernel. As I worked on it a little bit off stream, but basically this is sort of what we got going on. Have these two kernel threads running, and right now they're not exactly switching back and forth. The kernel sort of is just re-triggering them from each of their respective starting points. And so we have some work to do there, but at least it's a little bit of a start. It's basically just switching back between launching task 1 and launching task 2, and it just switches back and forth. So I'm pretty excited about that. Yeah, let me make sure that I update my title. Week 109. Yep. Okay, week 109. Updated that. What's up, Dimps12? Thanks for joining the chat. What's up, Abdullah? Hey, thank you. Hope you're doing well also. I'll get to that question in 1 minute. What's up, Sensei? Nice. Good times. Thank you. Appreciate that. Nice to see you again. All right. Okay, Discord message is sent out. Got the tweet has been sent out. I'm super excited about today, guys. I'm really excited. I think we're making some good progress, and I was really happy with how last week's stream went in terms of us getting started with our basic scheduling going on. And I think today will be a very interesting stream. I think we'll be able to let me refresh my Miro. Okay. I think we'll be able to get into some really interesting stuff today. Well, I think we'll be writing some assembly today. It's March 1st. We'll be writing some assembly today. We'll be doing some context switching. Stuff like this. So let's make a fresh plan. But first, let me answer this question, Dimst. Hi, I'm new to operating system. Oh wait, I also forgot to do my test 0 in the chat as usual. So, whoa, this is very interesting. Sensei's message got weirdly interpreted by the chat plugin, and it said good mark. So whoa, it interpreted the TZ as an HTML. Is that an HTML tag? No way. You can inject. Oh my gosh. So I'm not going to talk anything more about that because that sounds kind of dangerous for people to know about. So. Yo, what's up, Astro with Avarn? Thank you. Nice to see you. What's up, Sanam Preet? Yo, Honey Singh. Okay, I'll briefly explain what I'm doing. And so basically, I'm working on my own operating system. Marky, that would be crazy. Yeah, I'll leave that for you to experiment with, Sensei. Don't, use that knowledge responsibly. So I've been working on my own operating system for about 2 years now. And the first year of this was me following this MIT course, which is where I learned basically everything I know. And for about one year now, I've been actually starting over from scratch with my own operating system, building it up pretty much from scratch with a couple of key principles in mind of using modern C++ as the main idea. And we've just been building it up from scratch. I've worked on things like integrating with bootloaders. I've worked on some virtual memory stuff. We've been doing interrupts recently. And then most recently, we've been getting into basic scheduling. And the goal is to have, I just want to have my minimal sort of goal. Yeah, I'd like to, I don't have it written down very well. I just want a basic kernel for the first step, which can do kernel threads with preemption of kernel threads. I'm not really interested in user space. I want to have some basic drivers, and I want to have some unit tests for the kernel, stuff like that. So that's sort of the idea. So without further ado, let's sort of kick it off. So today it's all about kernel threads / scheduling. What's up, Devin? Chill. What field do you work in as your professional job? I work in the music technology industry. So I work on hardware devices for producing music and performing music, mostly electronic music, that kind of stuff. So, a basic single task. So this was the absolute baby step that we started with last week, and then now we can take a few more steps for that. And so switch between two tasks, aka just relaunch them. That's also sounds cool. Good luck to you in the future. Thanks. No problem. Thanks for joining. And so this is what we've kind of done so far. And that's what we're seeing over here when I run the kernel. Let me show you the code. And so let me just clean here all this up. Okay, so we need to look at the scheduler.hpp. So what's going on right now is, so we need to look at kernel.hpp. Yeah, so basically what's kind of going on is this is the run function of the kernel, which, just to illustrate, the kernel, this is the k main, and the main, I'm trying to make this very small, and so basically I'm also trying to do this object oriented, which is maybe a very controversial idea, but yeah, so it's not like very advanced, but I just chose to make the kernel object. So now there's like this kernel object, and then instead of like adding a bunch of code here, we just do a run. And the only thing that really happens right now is we have the scheduler, and we just create two tasks, task 1 and task 2. And then we call yield on the scheduler, which basically means, okay, kind of choose a task and jump into it and kind of kick things off. And so the kernel basically just like loses execution after this point. Basically this like never really returns. And these tasks are super simple. I'm trying again to do the absolute like most simple version of this. And so the absolute most simple version, why are my tasks? Interesting that my IntelliSense could not find task 1, which is a little bit annoying. Interesting, but yeah, like modern Terry Davis, Templeless broadcast, trying my best. Try my best, yeah. And these are just functions. Right now, kernel tasks are literally just these functions. It's nothing fancy. It's nothing like, there's no elf loading. There's no user space. It's just kernel. It's really kernel threads. Everything runs in the kernel. But for the first time, we're introducing discrete threads or discrete strands of execution, basically. So, yeah, that's basically the context. Yo, what's up, Digitalized? Nice to see you as always. So we create 2 tasks. I'm going to reset the timer. I think it was a bit too soon for a timeout. We'll get into that a little bit later. And then we hit the scheduler, and then we just sort of jump into things. And then let's look at the implementation of yield. So, yield. So, what does yield do? We look up the current running task if it exists, and it might not exist if we are in a freshly created scheduler instance. We don't exactly have a currently running task, which is why it's like kind of conditional on the current task. That's sort of a TBD thing. I don't know if there's a different way I could design this. But yeah. Let me also update the OBS, the top text. We're not doing interrupts anymore. Exactly, we're doing scheduling. All right. The pop out chat. What's up, Jai Rivankar? First time here, I want to ask if I were starting to build my own OS now, where to start? I'm going to link you to a couple of things, the resources, also the MIT course. I'm not sure if it's on there. Harvard CS61. Yeah, those would be my initial recommendations for you. I'll also say one thing I have in the works is I'm sort of planning on releasing a sort of like a subset of my OS. I'm sort of planning on releasing like my build system and like all my base infrastructure for setting up and getting started with the OS, but then probably not my actual OS code because I don't feel so comfortable with that or confident with that. But I think that would also maybe be a decent point if you're trying to learn about this stuff. If you are interested in learning more about and following on with updates for this release, you can follow my newsletter, and I'll be posting updates about that there. So you're going to do yields, so cooperative multi-threading, assuming your tasks are well behaved for now. Exactly. So yeah, that's specifically what we're doing right now. We're doing cooperative multi-threading or multitasking, which doesn't mean I will never have preemptive multitasking, but I sort of view it as a prerequisite. And as far as like simple starting points, it's a really nice basic checkpoint to reach because it doesn't require an interrupt, a timer interrupt or anything like this, but we can still work on some of the core data structures, core mechanisms of storing the tasks, fleshing out the task structures, getting the scheduler APIs set up. But then yes, the caveat is that the threads need to be well behaved for now. But I do plan on adding preemptive multitasking for sure. This is just a first starting point. And it's also, it's not like you could skip this part. Like, you can't just skip having a yield function in the scheduler. There's going to be times when, for various reasons, like in kernel threads, you just need to deschedule a thread and then yield to the scheduler. And so what we're doing with this yield stuff, it's not like it's wasting time. I would view it as a prerequisite for anything more advanced we want to do in the future. So that's why I'm choosing this as a starting point. But I could be wrong. I don't know. Maybe I'm not an expert, but like this is just sort of my current state of understanding. And it allows us to focus on the key concepts here, which is like scheduling between threads. So yeah, right. Got to save them registers. Exactly. In any case, you gotta save the registers. And so speaking of registers, let's get into that. So basically just to finish the overview of how this works so far, I got the yield function. It looks up if there is a current task, and if there is a currently running task, we set its state to be runnable as opposed to running, because we're sort of setting up to like run something else, and so we don't want to have it be in a running state anymore necessarily. And about the current task thing, so basically the only time this if will ever like not run is the very, very first call of yield, because that's when the fresh scheduler has been constructed and it doesn't have its current running task index set yet. But any other time it's going to have that set. So there might be some opportunities to redesign this a little bit, but that's how it works for now. I'm also going to take a note while I'm thinking of it. So some notion of the idle thread is probably going to be a good one. The idle thread is like the thread that runs when there's no other available threads to run on the system. And we don't really have that idea, that notion yet. But that would actually be one way to solve this issue, is that when we construct the scheduler, our container of tasks is going to be pre-initialized to have one task in it, which will be the idle task. And then therefore this thing does not have to be an optional. It can just be initialized to 0 to point at the idle task. So anyway, that's getting into more like a bit more in the details that we don't need to care so much about yet. But then now we go and we use the policy to choose a next task. The policy is why is my Clang D is like kind of messed up. I don't have a good solution for this. Right now I need to manually edit this Clang D file to switch to make it understand the includes for restart Clang D, I think. For what I'm building for the target architecture, or the target platform. But what I've done is I basically made the scheduler a template for now. And when I construct the scheduler, I'm actually making a round robin scheduler, which is this. It's a scheduler with a round robin policy. And then I chose to use this the policy, I don't know, a design pattern or whatever it's called. I don't really know the design pattern so well, but basically it's this template. And so I can sort of plug in different policies into my scheduler. At compile time, maybe it would be useful to do that at runtime, I don't know. But right now it's this compile time thing. And then so the logic for scheduling is removed from the core scheduler. And the core scheduler just has sort of more generic logic, and then the details of exactly how to choose the next task are delegated to the policy via this choose next task API. And then in our round robin policy, is meant to be the simplest policy possible, and all it does is it pretty much just like linearly iterates through all of the tasks looking for a runnable task and returns it. And And if you can't, and if the scheduler cannot find any runnable task, it returns a null opt, which is why there's an optional here. And right now we just assert, but that's also a reason to go with the idle thread, because if we go with the idle thread that just always exists in the tasks, we don't ever need to worry about not being able to find a runnable task, I think. So, and it could potentially even simplify this API maybe. So yeah. Anyway, that's how it works. And then lastly, switch to task. It's kind of unhinged right now, but I just have like some inline assembly that switches the task, and all we do is we set the current running task index to the index that was chosen here by the policy. We look up the task, we set its state to running, and then we just drop into the inline assembly that basically resets the state and jumps into the task. And to be more specific, it's taking the task state, it's taking the register state. So the register state is the struct that contains all of the registers, and then we are just sort of like unloading each of these members into the appropriate registers. And it's important that the order here like match it. It's important that we like never reorder this list, which is like a little bit unfortunate, but whatever. And there's a couple of like little tricks here. And so jumping to the RIP uses like this little trick called, I think it's called, it's like you use a push and then a return to jump to an arbitrary program counter without using a register. Like typically you would just do the normal indirect branch instruction, but that requires a register, and here we've consumed all the registers. We don't have a spare register, and so we can use the push ret trick to jump to the PC. And then the last trick is it's not really a trick, but what I want to do is I want the tasks to receive a pointer, or really it's a reference to the kernel. So then tasks should basically just be able to do anything like anything that the kernel can do, basically. And I'm trying to avoid global state in my kernel. And so in order to avoid global state, I'm passing in a reference to the kernel to every task. So in order to do that, I need to specifically make sure that RDI gets set to the pointer to this like kernel thing. Is that second to last instruction the PC? Second to last instruction, you mean this? The move R15, that is setting R15. No, this is the PC, and so offset 78 in the struct is where RIP lives, and so we're pushing that onto the stack, and then returning. And then then we have to set R15 at the very, very end, because R15 is in use this whole time as the pointer to the register state. And so that needs to be intact until there's no other reason to reference the register state. And so we can only set that at the very, very end. So I hope I just answered the question why it's after the push. It's because if we set R15 before the push, R15 would point to whatever R15 in the task is, and that's not what we want. And so it's a little bit delicate. The ordering there is a little bit delicate. It's probably worth a comment. I mean, the fact that you need to think about this is not so intuitive. Need to set R15 at the end because it's in use. Because otherwise it's in use for referencing the register state struct. So Wilson Barbosa, any books? I mean, I really just need to say, I personally have not read a lot of books. It's really been like, I can't stress enough how much like the MIT course helped me with this. What's up, SJAWWJ? Did you finish the whole MIT course all the way through, lectures? So what I did is I just did all the projects. And I did not do any extra credit. I only did the core projects in the course. And the assignments have a lot of like documentation and instructional material. Yeah, there are to be clear, there's no lectures. You don't get like videos or anything like that. All you get is basically just the assignments and some of the course materials around the projects. But for me, that was actually more than enough to learn a lot. So, yes. Okay, let's, so what, and so basically that's just to explain the current state of things. And so what you'll notice, and what's very critical here, currently, oh, they got the lectures on YouTube? I think I knew that. I think someone had told that before, but I don't know if they were for this version of the class I was taking. I think they are for maybe a later year. You know, I think actually Digitalized told me about this. Digitalized took like the 2020 version of the course, and I think he was referencing some lectures. Personally, I never watched the lectures, and because the course materials were good enough, I didn't need to. And I also maybe had a bit of background knowledge where I didn't need to. So, okay, so there's one thing that's critically missing here in our context switch. And what is absolutely critically missing is we never save the state of the task. What's up, Alavane, KI Prince, complete new Bakuna, but here for the vibes. Well, you're absolutely welcome to join us for the vibes. Where's my water? You're absolutely welcome to hang out. Just gonna kick it. So we need to save the state. What happens right now is we never save the state of the task anymore. All we do is just like hard overwrite it to whatever is in the task struct when it gets created. And that's going to be determined here in the create task function, which is where we construct the task. And we basically construct an empty task. We only set the RIP and the RSP. So we set the RIP to the first instruction of the task. And then we set the RSP to the per task stack area. And that's literally it. And so the consequence of this is that we're like jumping into the starting point of every task over and over again. The task, so the tasks hit, like task one starts it says hello, it logs this, it spins a little bit and hits the scheduler. The scheduler selects task 2, which executes down here, says hello, spins a little bit, hits the scheduler, which goes back, selects task 1, but currently the scheduler is not able to resume task 1. We haven't implemented that yet, so all that happens is we just restart at the beginning, and Sensei asks, is the reg state all zeros? Yes, except for RIP and RSP. Those get set to the initial starting state. RIP and RSP are set to point to the starting point and whatever, but otherwise everything else is zeros. Since we're not populating the struct. Yes, everything is zeros. And so I have a default, great. I'm using this, I have a constructor, and the kernel reference. So there's a couple exceptions. So yeah, basically everything is 0 except for the RIP, the RSP, and in the RDI, we explicitly are setting it to the context pointer on the entry point. And you know what, that is actually an interesting edge case that I hadn't quite thought about. So on the initial entry point into running a task, we need to set RDI to be the context pointer, but otherwise we need to make sure to not do that actually. So that is actually a bug. So let me take a few notes of things we need to do today. So fix the RDI bug, only set RDI on the initial entry point into the task. So I think actually, Sensei, you found a bug, or pointed at a bug. This is an implementation of switch that only works for for calling into a fresh task. So that's a bug. And we need to store the task register state. And the idle thread can come later. All right, so I think I'm going to start with this one, and I'm going to do that after a 20-second break. Feel free to stand up and stretch, get some water, whatever. Be right back. All right, so let's kick it off. So yeah, the bug is we should not be doing this here. What we actually should be doing is, whereas our RDI is after RDX, and so right here it should pretty much be hex 20. And then we no longer want to be setting this. And so now the question is, how do we make sure that we pass, how can we pass the context pointer? And the way we're going to do that is by constructing it into the register state. And so what else? Yeah. For T, P context, RDI, P context, something like this. Why am I getting a? Oh, okay. Got the. Oh, okay. Got the warning. Can't you just pop it in every time? I don't think so. I think because the task could be using RDI. Well, I guess it depends on what. Maybe I don't quite understand. Can you pop it in every time? Where you and the idea is we want this context switch to be a pretty generic context switch routine that we can use for normal switching even after tasks have started execution. And so it's critical in that case that we're restoring RDI from the context struct. And so I think I don't understand what pop it in every time means, but the way I'm thinking about it right now is that when we create the task, we need to for it to reinterpret cast. We just need to make sure to initialize that correctly. So this is my current thinking of how to do this. We're going to initialize the register state with a couple of things, RDI, RIP, and RSP. And then that's going to still work because here we're just going to generically load RDI from the state, which is pre-populated correctly. And this should still work. Let's just make sure this still works. We should see it going back and forth. Then how would the task find a reference to the kernel to store? So the register state, and how would the task find a reference to the kernel to store register state? To store the register state. I think maybe let me explain how I'm planning to solve that part. So, I mean, what we're going to have is when the task is running, it has the reference to the kernel. And it's going to call, like its registers are just set up in a certain way. If it clobbers, right, and that's the thing, it's not going to clobber the reference to the kernel. It's important that if a task, if a task wants to keep using the kernel, it cannot overwrite that reference. So a task is going to need to store the reference to the kernel somewhere so that it's in a register. And then it will automatically be saved and restored correctly. So that's how I'm thinking about it. Olivan, were you previously a software engineer / developer? I currently am, in fact, a software engineer or developer. I am not yet a full-time influencer or content creator. I very much have like a job, and I'm a programmer at my job. I'm not an OS programmer at my job, though. Maybe I can try to illustrate what I mean. So let's yes, yeah. So basically, yeah, Sensei. So my responsibility as far as the scheduler, if I'm the scheduler, is my responsibility is I'm going to construct an initial register state, and my responsibility is to pass this pointer into the function, and that's where my responsibility really ends. The task is going to execute whatever code it wants, and then as the scheduler, I'm just going to make sure that whatever it's doing gets perfectly preserved and restored, and including whatever pointers it's using. And so, for example, in this loop, let's just imagine a working version of this scheduler where it actually is able to resume from this point correctly. I'm pretty sure that RDI is just going to stay, like the kernel pointer is just going to stay in RDI the entire time. And so when we save the state, we're going to just save that RDI, and it's just going to be the kernel pointer and restore it just like normal without any kind of special casing around this. So the first baby step I'm going to take is what could that be? Because, okay, so I'm just gonna say this is working. So this got fixed. I'm just thinking about, it's a little bit weird that I'm doing this in inline assembly. Okay, I need to think a little bit about how this is going to work. So when yield gets called, you know, I don't actually think we can do it like this. Let me think about this. So this was sort of the easy part. We're executing arbitrary code, and then we just sort of like hard overwrite into the task. To actually yield correctly, we need to make sure that we are perfectly preserving the register state, which means we cannot just be like running arbitrary code. I think we actually need to make that directly call into assembly. Otherwise, like the epilogue is gonna run, or the prologue is gonna run, like who knows what registers we're gonna lose. And so I think I'm gonna make, dang, I did not mean to do that. That was weird. I'm gonna make a scheduler.s just to kind of get us going. Or maybe I can copy it from trap.s. We already have that. Scheduler.s overwrite. I don't know. I need to remember even how to like do anything with assembly. I think we don't need this anymore. We don't need this anymore. I just want to have a basic function. And so let's just do this. Okay. It's going to be called, it's just going to be called yield. Right. Jump yield. Just for purposes of being able to, like, let me just check if this even compiles. So I need to add this over here. Scheduler.s. And now that means we need to have a function prototype. I'm just going to call this yield right here. And then now we're just going to call this global yield function. And you know what? I actually don't like the name. It's a bit too opaque. I'm going to call it scheduler yield to be slightly more clear about that. Scheduler yield. And maybe we'll even, okay, name the bike shedding over the name is not necessary at this point. I was even thinking if like assembly scheduler yield would help make it clear that we're calling into an assembly stub right here, but that's not the most important part. I'm just going to just see if this compiles. Are we even compiling? No, undefined symbol. Reference by, okay, something, scheduler yield was not found as a symbol by the linker, which suggests, oh, I think I need the extern C. Yeah, that's probably it. Okay, good. So now I just want to have a basic stub here, and my expectation is, I think we're just going to hit an infinite while loop. Quick chat on the chat. 18 people in the chat. That's a good one. Good day for the chat. Okay, so I'm gonna run the kernel now. Here's what I expect to see. We're gonna see hello from task 1, and then nothing else. It's gonna spin in scheduler yield, and that is just gonna help me make sure I have like this stub working. So good. So the stub's working, and so we've got the stub, and now we need to think about what to do. So this is maybe a little bit tricky. Maybe I need to think through this a bit more. So we need to save all of the registers somewhere. Well, eventually we need to save them into the task. Let me see. We need to save it into the task. Let me. Okay, I'm just gonna. Eventually we need to get the task. We need to get the task. How do we get the task? Well, okay, as usual, I'm gonna start off with the stupidest way I can think of doing this, and then maybe we can refine it later. Yeah, I need, like, once I can find the task, yeah, we can put the state into there. The problem is, how do we find the task right now? The task is somehow buried. It's like somewhere in the kernel, it's in the scheduler. Yeah, so again, I don't really know some of the answer. We need to get the task, but how? Get a pointer to the current task struct, but how? Yeah. something int a. Okay, stupid way. So what? Here's my plan, and basically I'm just sort of taking inspiration from how like normal interrupts work, where it's a very similar situation when an interrupt happens. Like we can look at trap.s for inspiration. When an interrupt happens, it freezes the program's execution. It stashes rip somewhere. Like rip gets stashed, and then it jumps to a special, like one of these special stubs. Okay, I'm just gonna work through this. So one, we need to locate rip and stash that away somewhere. That's like ultra important. And so the thread was executing in some kind of way. Maybe it helps to I'm just gonna check out this. Maybe it helps to illustrate this with can I find task one? So maybe it helps to illustrate this a little bit. So here's like call scheduler yield. Oops, task one. Okay, maybe this is not the best example, but I think it still is workable as an example. All I'm trying to point out, let me see if I can get an arrow. So here's our arrow that helps us see where rip is pointing to. So ignore this. Let's say this was actually the call to scheduled. Our job is to make sure the program is able to return and continue execution at the instruction after the call. It needs to have everything needed to resume at this function. So therefore, it's one of the most critical pieces of information is that we preserve the pointer to this instruction. You can't smuggle kernel, so maybe keep it as a constant address. Yeah, I think I'm not sure. I think there. Yeah, that's. I'm gonna stash that idea because that's an interesting idea. So maybe just we're getting a little like slightly ahead, but the problem. How do we locate a pointer to the task struct? We need to save the state into it, but when we get control in yield, we can't assume anything about any register in use. And so I think my stupid idea is one, simply just save all the state somewhere in memory, like on the stack, or maybe in some global struct that's used only for this purpose. Maybe that's a little bit safer than doing it on the stack. So we're just going to like blindly save all of the state somewhere. It's not going to be in the task. We don't know how to get the task yet. And so we're just going to save the state somewhere. And then once we've done that, we can then safely return to execution in C++ and figure out the rest of things, e.g. how to find the task and copy the state into it. That's my idea. Yeah, constant address that is a possibility too. Yeah, I think we'll play around. I think this is how I want to start out with, but basically what you're suggesting is more on this side of things, like, okay, how do we get this? Well, basically, once we've stashed the state, we can do scheduler dot current task, actually. So it's not really hard, actually. Once we have a pointer to the kernel and to the scheduler particularly, we can just call current task. But the question is how to get a pointer to the kernel? Okay. So it's easy to get the task if we have a pointer to the kernel. But how do we get a pointer to the kernel? Well, luckily, the kernel is a global object. Well, kernel is a global object. So we can probably, I don't know how exactly, I mean, we can just link it with an extern or whatever. It's actually not that hard to do. So I think that's the idea. Let me just check the chat. What's up, Starship? Mid-level Go, Python engineer here. Would I catch on OS low stuff if I watched all streams? No hard OS, but love your stuff. Well, thank you. I think I'm not sure I would recommend my streams as the only way to go about learning this. I think what I'm doing here can be useful as a supplement, but and it can shows you some, and you can definitely learn things, I think, from the way I work, but I think you also need to have some kind of more direct learning route via like reading one of those books that's been talked about, or following the MIT course or something like this. So I would recommend a dual approach. I mean, absolutely hang out with us, and I think, I'm happy to answer questions and stuff, but I'm just sort of I'm cautious to say this would be the only resource. So you're doing great. Thank you very much. Appreciate that. Nice Kirby plushie. Thank you, Koru. Definitely a fan of Kirby over here. Okay, let's try to do the stupid idea. I think this could work. Let's try. Yeah, okay. Basically, and then let's flesh out the idea in a little bit more detail. And so again, like, let's pretend this was like some stream of execution. Pretend this is the call. I'm just gonna maybe overwrite this yield. For the sake of demonstration, this is the call to yield. We're gonna get control in our assembly stub, and our key responsibility is to make sure the program can keep executing from specifically right here seamlessly, which means we need to, first order business, we need to save the RIP. We need to get this address somewhere. And so let's break that down into more detail. So simply save all the state somewhere. Let's talk about that. And so top priority number 1, save the RIP. And to do that, we're going to need to do that, we can read it off the stack, because when, just as a basic refresher of how this works, let's say we have some, why are these lines so skinny? Okay, let's say we have a stack frame for a function. Let's call it task 1 stack frame, and then a call instruction happens. It's going to execute a call instruction. It's going to do one thing immediately. If I can draw the line, it's going to saved RIP, e.g. to that move instruction. And so when it does this call and our assembly code gets execution, this is going to be the state we see. Why is the text is upside down? Okay. RSP is going to point right here. And so we can read, if we read RSP, we got the RIP. Probably want a function that returns a ref to the kernel. Yeah, that's probably a good idea too. Yeah, that could be a good idea. Yeah, either way, I think like using the extern or using the function. Yeah. All right, 20-second break, stand up and stretch and get some water. We'll be right back. All right, so what's up, Bishwas players? Nice to see you, my friend. We are deep in the weeds right now. We're about to get into some exciting stuff. And so we're talking about how do we safely implement the scheduler yield, where we try to save the state of a task. And this is our starting point. The first order of business, we got to save the RIP, save the instruction pointer. And we know how to do that. We can read RSP. That's going to return us the RIP. And so I'm going to save the RIP, stash that somewhere. That's the most vital piece of information to save, because that's immediately going to get basically clobbered in the actual register state as soon as the call happens. Kernel field also dump registers to task. Let me just keep fleshing out my idea. So once we've done that, the question is where, and what about doing what GS does? Chris Jaden, what about doing what GS does? Could you elaborate? I think I know what you're talking about. You're talking about the GS register and having it point to somewhere particular, like a known struct or something like this. Maybe that's a good idea. Yes. Maybe you might be more knowledgeable than I am about this, but okay, the question is how to get a pointer to the kernel, etc. And so there's a couple ideas, the global kernel address, the GS register, something like this. Yep. I think I don't understand this quite well enough. I mean, the GS register, from my understanding, it's like this long-lived register that doesn't really participate in I mean, it doesn't exactly participate in scheduling in the same way. It's like per CPU core or something like this. Yeah, that could definitely be a possibility. Maybe you could help me clarify what that means exactly. I think my current idea is, what if we just have a some global struct somewhere. GS register per CPU state. Let me, yeah. I'm gonna, yeah, I mean, stash that somewhere. It could be the stack, global struct, maybe. I'm sort of uncomfortable with doing it on the stack. Because there's always a risk of running off the end of the stack. But now that I think about it, I don't even know what happens when the CPU pushes some data on the stack during an interrupt. And I don't actually know really what happens if what happens if CPU tries to push data on a stack during interrupt and it goes off the end of the stack and faults. Smuggling approach, like a global struct. Yeah, I'm thinking let's just try this. Let's just sketch this out. And so we're gonna have the scheduler. And I don't even have a scheduler.c. Do I have a scheduler.cpp? That is in a third-party library. Okay, let's make a scheduler.cpp. Scheduler, and what we're going to do is I'm going to declare a global register state. Do you upload anything on GitHub? Not currently, but I'm thinking about it. If you're interested in the future GitHub release, please follow the newsletter. I'll be talking about updates there. So I think we're gonna have a global register state. Task register state. Register state, or maybe I'll call it the context switch register state or something weird like that. And okay, it's complaining because I don't have a default constructor. So let me just do that. Or equal default. And I think that works. So let's try this. We're going to have the global register state, and we're going to need the extern. We need to extern this. So other translation units can find it. And then, for example, that's what we're going to do here. Somehow we need to, how do we do that, actually? I genuinely am going to ask the AI. I want to get a pointer to the, in this assembly file. How can I do that? I'm gonna switch to the, I don't know, go with Sonnet 4.6 or something like that. Shouldn't that live inside the task struct in kernel? It does, but this is a special one. Okay, I'm using Intel syntax, please. So yes, the task register state absolutely lives inside the task struct. This is not a normal register state. This is explicitly for the purpose of being a temporary zone to save the register state at the start of the yield, which is currently how I'm thinking about doing this. We need to save, like, we know what to do, at least for this first step. We need to read RSP, but then we need to write that somewhere, and the question is, where do we write it to? The stack feels a little bit sketchy, and so we're going with this global struct option, and then the AI is saying you can just use variable names? What? Okay. So now let's write some assembly. And so what is it going to be? We're going to okay, here's where I don't know how to write assembly well enough. Shouldn't the current task be at a constant address? So I think with that idea, we would need to have some kind of like global pointer with a pointer to the current task. And I think that is actually sort of this GS idea. Global pointer to easily find the current task. Global pointer probably per CPU. And yes, and so I think that is maybe another interesting option here, is as an alternative to having a temporary global register state, it'll be something like this. We have a global pointer to current task or something like this. That is perhaps an idea. And that would mean that in our assembly, we can well, the thing is, we already have a global pointer to the kernel. That's the G kernel thing. Then the current task register state to be a field, maybe. For the moment, let me just try to do it this way, and we'll see if it can work. I think this is a decent approach. So, and then now I just need to, how do you, I'm feeling pretty stupid right now. How do you, okay. Now I want to dereference RSP and write that to register state. How might I, what instruction to do this? I feel kind of stupid. You can tell I don't write assembly because I just don't know how to do this. And so, okay, so, x86 can't do memory to memory moves directly, so you need a temporary register. Ugh, okay. Unfortunately, we don't have a temporary register. In this context, I'm running instructions at the start of a task yield, so I can't perturb any of the registers. Do I need to use the stack? I can use a global. Wait, that's such a good idea. We can have another global. That's actually genius. Okay, so that would be another idea. Before we get to whatever the AI suggested, which might actually be like a smart way, we could have another global just for the purpose of doing that. Right, so it would look like this. It would look like, just for fun, so we move global rip storage, and then we're able to then move. Wait, but we still need a register. Yeah, we still need to use a register actually. So it doesn't solve the problem. Like, we can save it into this place, but in order to move it into global task struct, this thing needs to be a register. So I actually, now that I don't quite see how that would work, but I think the AI did have some help. We don't need the stack. Since Rax is the first field, you can save it directly, then use Rax as your scratch pointer for everything else. Wait. Why is it using RIP relative addressing? Is that the canonical way to do this? Okay, let me understand since Rax is the first field, you can. I see. Okay, so the idea is we can just start like saving stuff into the state, and then that's going to free up some pointers, which we'll be able to use for saving the RIP. So let's try that. And so it's going to be like move. Let me. Rax. Does this compile? Undefined symbol, but if I have a syntax error, it does compile, right? Yeah, okay, cool. So now it's complaining about undefined symbol, because I think I need all the extern C. Does this work? No. Oops. Okay, am I like bugging out a little bit? How? Let me put kernel dot. How do you declare? Do I need? I don't need the extern here. Okay, if anyone knows the answer, feel free to let me know. Why is it not we're using this symbol. Do I need wait, do I need to do a rip relative or something weird like that? No. Okay, I'm gonna again have the AI help me. The linker cannot find the symbol. Any ideas? Oh wait, oh, it's probably because I forgot the CMake lists. We need scheduler.cpp. That's gonna do it. Yep, that's the reason why. Stop. I'm pretty sure. Let's try that one more time. Okay, no way, really? It's saying we need the extern here too. So okay, still having the problem. I made sure to add scheduler.cp2 current.c make lists.text. I wonder. You know, I think like this feels kind of weird to me. Yeah. I'm not an expert in this whole extern C thing with this, like, yeah. Oh, but yeah, so we have this thing here. Okay, it's crunching through this situation. What? Undefined symbol. All right, let's take a quick 20 seconds, be right back. Okay. What? Are you kidding me? Is that really? There's no way that... Holy crap, that fixed it. What? Okay, do I need this extern C though? That's what I'm wondering. I didn't think I needed that. Yeah, I thought you only need the extern C on the thing in the header. So this seems to be working now. I'm just going to quickly ask that question. I removed extern C from the CPP file and it still works. I thought you only need the extern C in the header. Is this true? Okay, saying I'm correct. So now let's let's just try this out. So I'm just going to debug the kernel. What? Oh, make debug. All right, so now I'm going to break on scheduler yield. And we're just going to run the kernel until scheduler yield. And there it is. Look at that. But something weird. I feel like it broke on the wrong instruction. Why? I feel like we're broken on the jump, but that's not the first instruction of this stub. So what is going on? Okay, that's whack. But anyway, I think that's good. What's up, Pretzelcat Gaming? Good morning. Whew. What's up, X Sour Ab Sharma? Which OS system are you are building? How can you check it is working or not? It's my custom operating system. Yeah, and how can you check it is working or not? Well, I mean, like you can, if you're talking about how I can check it, I can tell if it's crashing. I can tell if it's, I mean, there's a lot of ways that kernel can be broken. If it's bootlooping the machine, we're just taking it step by step. What's up, Martyr World from Vibe Coders? We have this guy building an OS. Well, don't speak too soon. I'm also at times a little bit of a vibe coder, but I try not to be almost all of the time. So I don't know if you would consider asking for help from the AI vibe coding. I kind of don't. I'm trying not to. My policy is I don't generate like a lot of code. I just generate small bits of code. So keyword pointer, that looks great. And so it why is that a negative? Is that normal for it to be negative? Not really sure. Oh, maybe because it's a, oh, maybe it's because it's a kernel address, which is a negative, and then that's funny, because it's going to be a kernel pointer which is technically like a negative address. So that is kind of funny. Let's just out of curiosity, let's print out. Oh, does it not tap? I was just curious if we can do something like this. Does this work? Okay. I have a stupid is the same as. I'm just gonna ask that. That's, how do you even? Okay. You know, that's cool. So that is all working. We're able to reference our global struct. Maybe I'm being a little bit stupid right now. I'm not, other than asking the AI and other than doing the math out and flipping all the bits, I'm sort of blanking on how you would even confirm that, and without like writing like a C program that does some casting and stuff like this. How could I verify that myself with Python? -1 to 64. Okay. that makes sense. Let me just do that. Not that I don't trust the AI, but man, how do I get rid of this? EE620. Does that look right? That looks right. Okay, cool. So, yep. Not using AI is not bad. I think that's a power tool. Yeah, agreed. Here for the first time seeing your video on my YouTube channel. Like, subscribe. Good luck, man. Thank you very much. X-Hour Absharma. Appreciate that. What do you think of Terry Davis? Like his work? Yeah, I think it's very impressive what he's done. And I would say, yeah, he's an inspiration for sure. Okay, cool. So now that we got that, so that's pretty cool that we can just use symbols. I do like that. So now let's just try to do this. And so we're just gonna I wish there was a better RDI RSI. Dude, what are the registers? Okay. RSI, RBP. R8, no, R8, R9, dang, R10, okay, 11, 12, 13, 14, 15, okay. Sorry if that was a little bit excruciating watching me type out a bunch of stuff. And so, and then then we have at the very end of the struct, RIP and RSP. Okay, so RIP and RSP at the very end. And again, let me just try to get these offsets correct. Switch to task. So 8. Okay, I need to type better. Am I getting this right? No, I messed up. What? 18, 20. I'm missing RSI. Okay. Okay. RSI 28, 30, 38, 40, 48, 50, R11, 58, 60, 68. Okay, here's where it gets interesting. R15 is at 70. RIP is at 78, and RSP is at 80. Okay. Thank you, Starship. Really appreciate that. Okay, so So here's the basic idea. It's like sort of like phase 1, save all the easily saved registers, which also frees up some registers. Right. Okay. So now, I mean, also RSP, I think, technically is kind of easy to save. The only thing is then rip. And then now to save rip, phase 2, save rip. And then now we need to actually start clobbering some of the registers. And we're going to, oh shit, but wait a sec, okay. This is slightly different. So this is not right, wrong. Okay, let's start one at a time. Rip is a little bit easier to save. We need to save RSP into racks, and then we can move racks into offset 78. What's up, Twix XX? Not currently, but if you want to hear updates about the GitHub release, please join us in the newsletter, which is where I talk about that kind of thing. Phase 2, kernel plus task reg field offset. almost not quite, but almost. Let me just see. Phase 1, save rip. Or phase 2. Phase 3, save RSP. And so the thing about this is we actually cannot just do this. What's up, Azure Tron Line? Are you going to make a Linux distro? We got an Arch user. Everyone, stop what you're doing. We got an Arch user in the house. I'm personally not planning on making a Linux distro. I'm just making my custom kernel for the moment. Yes. Coding Banana, what is up? Nice to see you. Okay, RSP. So here's the thing. Let's talk RSP. So I was tempted to just put this here. I was tempted to put save RSP into the offset just like everything else. But here's why that's not going to work. The thing is, because RSP is pointing right here in the stack. If we think about our example here, we're trying to restore the exact state of things such that we can resume seamlessly here. And we need to and at the state of the call instruction, or basically right before the call instruction, RSP was pointing here. So we need to actually do a small adjustment. We need to make sure that we're not saving RISP directly. We're saying RSP plus 8. So yes. What's your opinion about Rust? Why do you use C++ instead of Rust? I think Rust is a great language. I actually really wish I could use Rust. The reason why I can't use Rust and why I don't use Rust is because I do not know Rust, and I do not, and right now is not the right moment for me to learn Rust. Right now I'm trying to learn operating systems development, and I'm already very, very familiar with C++, and C++ is completely a usable language for whatever I want to do with OS development. And there's really no good reason for me to learn two hard things at the same time. I wanted to focus on learning one hard thing at a time, basically, which is why I'm using C++. Yeah. Yeah, I don't know. I don't know if C++ will always be the best, to be fair, but it's just what I know, and I'm just going with it. But there are so many things I do not like about C++, and I would really love to use Rust, but that's just not where we're at. And also, for the record, I was actually just really curious personally about what it takes to use C++ in a freestanding environment, and so that's also just a personal curiosity for me. Oh, we got NSG in the house. What's up, NSG? Yes, we are deep in the context switch right now, and we're talking about how to save the RSP, and how do you even do that? Is it something like this? Is there a better way to add 8 to a register? Is there a better way to... I want to read our RSP, add 8, then save it to memory somewhere. Is there a better way? Is LEA is the goated way to do this? Yes. LEA is the goated way to do basic math like that. NSG, leave an IRET. Well, yeah, we're not using IRET at all right now. I mean, like in this case, we're switching between kernel threads, and so there's no IRET at all actually, and for what we're doing right now. So I think this is what we want. Honestly, C++ is awful. I agree. C++ is really awful sometimes. I really agree. Okay. So let's talk. Save one instruction. Okay. So this is decent. So we got our yield. So we've sort of populated this global register temporary scratch state kind of thing. Actually, I'm going to rename it to that, I think. It's really, that's what it is. Context register scratch state. It's kind of a context switch. Yeah, whatever. So we got our context switch register scratch state. It gets populated with a couple things. And now how to call into C++. So how do we do this actually? So we can call a function. Yeah, I don't know. I think something like what? I think I need another like global function or something like this. I think I need something. Wait, okay, I'm just gonna yield entry point kernel something like this. dang, okay. I was hoping to not have to have any dependency on the kernel, but okay. So we have the yield entry point. What's this thing called? This is the scheduler yield. Then we have scheduler yield entry point. And then what can we do? We can RDI this and then call. Oh, dang. Ugh. I wonder. I wonder. And then that would let us, then that would get us over here, at which point we're back in C++. And then can call back into the scheduler somehow. So I wonder. Okay, this is like kind of weird. Panic. Okay. Back in after yield. Okay, let's try this. WTF, dude, what makes you so dedicated into this project? 109 weeks is an insane amount of time. I just really like learning about OS development. I think it's super fun. And it's fun to hang out here with you all. That's super enjoyable for me. So it feels fun, honestly. NSG, a better idea. NSG with the good ideas as always. A better idea would be to push the context on the stack. Since in an SMP system, this global context structure could get corrupted when many CPUs try to reschedule. Right, so obviously for multi-core, this would need to be per CPU state. But yes. The reason I didn't go with the stack approach is because what if we go off the end of the stack while pushing all the context? I don't know. Do you actually know how to handle that? Like, what would happen if the stack pointer is in such a situation where it actually faults as I'm trying to push all these things? That was the reason I did not use. But NSG, the thing is, there's no IST here. This is a kernel thread manually yielding back to the scheduler. So I guess what you're saying is there could be a dedicated stack. I don't quite know how that would work. It just seems like a little bit more complicated than having a scratch state struct, but maybe there is some way to switch the stack to a safe stack. But how do you save the stack? Like, let's entertain that thought for a second. How do you like? I'm going to kill the palm tree because we're getting close to end of time. How would I switch the stack here? Genuine question. Let's say the scenario is like this, where the calling thread called the call to the scheduler, our RSP points here, which was on a boundary, and so that is, and so then let's say this is unmapped, and so it is not safe to do anything with the stack anymore. No push is safe anymore. And like, so how are we going to switch the stack pointer? We would need to like move RSP safe stack or something like this. But doesn't that clobber RSP? Didn't we just lose RSP by doing that? So basically, that's why I didn't know. I genuinely just do not know how to switch the stack without clobbering RSP in an unrecoverable way. And so for me, that was like the pragmatic reason to use this global scratch state. At which point, I think we're like basically ready to test this actually. So let me just try to build. And as usual, I think the reason is because it was in a header. So let me try to fix that. Okay. Does this build? This builds. Let's. All right, let's just run it and see what happens. Yo, check it out. Back in CPP after yield. So I think that is nominally working. Just for fun, let's just hop through that in the debugger just to see that in action. Do you preserve the context in the task struct? That's the ultimate destination. Yes, it's not like currently it's in the global scratch area, but then we can just, we're going to copy that over into the task struct. So let's break here. So just I don't know what's up with LLDB. It like weirdly breaks on the second instruction, which seems buggy to me. But so we got our code lined up here. So let's just keep your eyes over here. We're just gonna step through saving all the things. We save the PC. Let me just wait. I think I want to verify this a little bit. I went a bit too fast there. Damn, chat's all right, yo. Unheard gamer, you gotta stop spamming the chat. Yeah. What? Don't post that message so much. I think I gotta put you in a timeout. I'm sorry. Dang, I've never had to time out someone before. I'm sorry I had to do that, but please do not spam the chat like that. Okay, let's break on task 1. So, all right, we're in task 1 right now, right? And what I'm specifically trying to see is, or where, task 1. Oh wait, oh my gosh, it's in kernel.hpp. So to verify that this is working, I want to step right up to this call instruction for scheduled, and we want to see a couple of things. So I want to, basically, yeah, I mean, we have, this is sort of the information I was looking for. So I'll just stash this. So I'm just going to break right on this instruction. Why did I feel like, okay, it took a, wait, that, why? Okay, something kind of strange just happened there. I feel like it didn't, did not understand that. Oops, wait, what? Break. Scheduler yield, continue. Oh shit, damn, I'm sorry. Break task 1, continue. And I'm also going to remove the timer because that's not really important right now. So okay, here we are. Here we are. Is it just me, or does anyone feel like a union function can fix this issue? Maybe just me. I actually don't know what a union function really is. So yeah, I think I would need a bit more explanation to understand that one. I feel like something is kind of weird. I think it's like I accidentally stepped too far, but I was trying to be pretty careful about that. Let me try one more time super carefully. Okay, super careful. Oh shit, okay. Next instruction. Okay, we're broken. We are broken at the BBC, right? Next instruction is gonna land us on the call. Right, okay, good. Yes, so I know what a union is, but maybe you can clarify how it fixes the problem we're seeing right now. Okay, so a couple key pieces of information. So the RIP, here's the RIP that we need to restore, the BC6. Also, RSP is pointed at 52FE8. And so that's the key part. This is the RSP that we want to save into the tasks, the scratch state, basically. So now let's step instruction. We're going to step all the way through everything. And I'm just going to continue. I'm going to break on scheduler yield entry point. I don't know. Why was that not? Okay, now we're broken on scheduler yield entry. Now I want to print the G, and for some reason that is not completing also. I want to print this thing. So I want to print dot rip. And we can see that we stored the B6C correctly in the RIP. And then let's do the same thing for RSP. we can see that we stored that 52FE8 correctly in the RSP. So that's looking great. And then now that we are back in C++ world, and also now that we have a pointer to the kernel again, we can so now we need to copy the state into the current task. And so I need to get so auto task equals kernel.m scheduler.current task. We also need kernel, and maybe I'll just do the okay. Yo, what's up, Tech Easy? Thank you. Okay, a near root gamer. I see you're again copying and pasting messages. I really have to insist that that's not acceptable behavior. I need to time you out for 10 minutes. Okay, so we got the task, and so now we got the p task, and now it's time to copy in from the scratch area. Maybe this is stupid, but can you do this? Obviously, if you were in C, then you would be doing some like mem copy, like BS or whatever like that. I'm trying to not program in C, which is like the whole point of using C++. And I think I just want to ask the AI just to make sure, is this equivalent to mem copying? The state. So yes, cool. Can you explain the whole scheduler working after you're done with this? Sure, yeah, totally. I mean, I do have to leave in maybe 10 to 15 minutes, but I'll try to give a little overview. Because yeah, it's like kind of right in the middle of things. Okay, so cool. So copy in the register state from the scratch area. And then what do we do now? We can like hit up the scheduler. We can like call into yield. I think we just, yeah, kernel.m scheduler.yield, something like this. Task state is no longer running. Yeah, and so when I call yield, we're gonna hit here, and it's gonna set the state to runnable. Dude, I wonder. I don't know. I wonder if there's anything left to do, or is this maybe gonna work? Are we gonna be able to switch between the two tasks now? I think there's a possibility that that's gonna work. coding banana. Are you closer to drawing windows and getting user inputs? I have to say that's still kind of a ways out. I mean, drawing windows, definitely a bit of a ways out. Getting user input, I think that's, that's probably a little bit closer. We could probably finagle some kind of serial console input or something like this. So in our switch to task, so now here we're just going to be generically restoring the state pretty much. We're not doing anything fancy with the context pointer anymore. All we're just doing is just restoring state. So I'm feeling kind of feeling optimistic. Let's just try this. Before we try this, let's just make sure. Okay, let's add back the sleep. And let's also add a counter. And we're just going to, let's get rid of this hello counter. Yeah, I'm just gonna duplicate that exact same thing. Counter, right. Obviously counter plus plus. Okay. So okay, we should be making sure to hit scheduler yield here. And if this is all working, we should see some interleaved output going back and forth between hello from task 1 with a number going up, hello from task 2 with a number going up. It's possible that this will not work and just will crash horribly, but I don't know. Moment of truth, let's run it. Damn, double fault. Fuck. Okay. That's not what I was hoping for. That is not what I was hoping for. Can we briefly debug that? Fuck. That's not what I was hoping for. Okay. Break in task 1. Step. Let's break on scheduler yield. Break. Okay. Let's break on scheduler yield entry point. Okay, so now we're in the entry point and it double faulted immediately. That's interesting. Let's do that one more time, but at the assembly level. So let's break on scheduler yield. I do not know why I cannot tab complete that. Okay. So let's be very clear about this. Okay, so we're here. Move RDI. That is okay. That is the kernel pointer. We're going to step instruction, right? So now add RDI plus some offset to get to the scheduler. Step instruction. We're going to call into current task. That did not fault yet. Okay, let's just step a couple more instructions. Let's check out what RDI is. Okay, RDI is screwed up. That's the problem. RDI is messed up. Why would that be? What happened to RDI there? That means I passed it wrong here. Something. Why? That means this was wrong. Something happened there. Let's just. We're getting close, I think. Also getting close to when I need to go, but I just really want to see this work. But no, I want to break on scheduler yield. You're passing this. Oh, wait, what? Oh, yeah. Yes, that is absolutely correct. NSG, you get the point for today. NSG with the sharp eyes. I was passing the wrong freaking thing. Okay. Oh, stupid. Okay. So now the P task assertion failed. What? Okay, but I think we're getting close. I think we're getting close. Debug. LDB. Break on. Okay, let's okay. PXG kernel. Damn. PX address of G kernel. Oh. What? Why are those different? Also, what? What? What the fuck? G kernel. Okay, something is whack. Why? Okay. Something about this is sus. Do I need to? What about LEA? I don't know. Maybe I need the LEA actually. That's like a little bit of a blind. Yo, okay, that was it. Something went wrong. I don't know what's up with move, blah, 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 blah. Oh, okay. Damn, okay. It's working. That's crazy. Oh my God. All right, some dubs in the chat, please. I'm so happy to see this. Game, yo, we are gaming right now, that's for sure. We are gaming, oh my gosh. Let me, thank you. I appreciate it. Thank you to all of you for helping me out. I feel like I'm pair programming a little bit, like NSG with the clutch save on the G kernel thing. I mean, y'all been like straight up pair programming with me this whole time. Look at how slow this is getting. That is not good. That's gonna be a to-do for next time. Something is up with that. Okay. Why is it getting so slow? Okay, I'm not gonna care about that right now. I'm gonna I don't know. Let me check out some of this chat. The higher it goes, the slower it gets. Something. No. Do I have something super stupid? Kernel.hpp. It sleeps the same amount of time for every time. So, I mean, that's so annoying. This is working so well. What could possibly be slowing it down the more it takes? We're not adding any extra tasks anywhere. Okay, maybe this is a good segue for NSG. Yeah, no, I can stick around for a little bit longer. So basically, NSG. What I'm doing here is I'm trying to implement the most basic version of scheduling at all possible. Literally the actual simplest thing. For me, what that means is like no user space, no interrupts, no changing address spaces, just switching between tasks within the kernel. So kernel threads, basically, all within the same address space, all within the kernel's address space, cooperatively scheduling between two threads. That's what I've been trying to do because I perceive this as kind of just a base prerequisite before more advanced things like preemptive multitasking with the timer interrupt or whatever. So yes, scheduling without the timer. To keep it really, really simple. I don't have a timer interrupt yet, and so I don't have a timer. But that doesn't mean I can't do some basic scheduling. And so that's what I've been trying to do. And so the way it works is, yes, cooperative scheduling. The way it works, when the kernel boots up, all it does is we create a scheduler instance. It's this round robin scheduler or whatever. And on construction of the scheduler, it allocates something super stupid. It's like this fixed size array basically with two slots in it. There's only two possible tasks on the system right now. And so we're going to increase that number eventually, but right now it's like this super stupid container of two tasks. And then a task is, I don't know, like we'll change this later, but it has like an ID and it has a scheduler state of whether it's runnable or running. It has its register state, which are the registers. It has a context pointer, which we'll get into, and then it has a stack frame. And so every kernel thread has its own stack. But otherwise it's in a shared address space. So that's really the only particular piece of like per kernel thread like state or whatever. And so what we do is on the boot up of the kernel, all I do is I fill both of those slots. I call create task twice. And the create task API looks like this. I pass in a function pointer, and then the create task API also takes a context pointer, and that is the pointer that is going to get passed into the argument of the kernel thread. And it's a void pointer over here such that like to reduce dependency on the kernel, but in practice both of the threads just pass the pointer to the kernel object as the context pointer. And basically, yeah, so we populate both of these two tasks. In order to create a task, we allocate a stack frame for it. We point rip at the pointer to the task function. We point RSP to the stack frame, and then we just basically put it into this container of the two tasks. We increment this counter thing, and we mark them, we put it into a runnable state, stuff like this. And then after so basically we would populate these two slots in the task storage, and then we call yield to trigger the scheduler. All that does is it finds the current task if it exists, sets the current tasks to be kind of deactivated in a runnable but not running state. It calls into the scheduler policy to figure out what should be run, and in this case I'm using a round robin policy, but we can plug different policies if we want, but it's just sort of architected like this. And this is just a super simple scheduler or round robin that looks through the container of tasks and just tries to find a runnable task. And then it returns a task index. And then once we have a task index, we switch into it, which involves updating our current notion of the currently running task, setting the state to running, and then switching into the task. At which point the task begins to execute, and then in this stream we just implemented support for like really returning back to the scheduler via this, and trying to design like how this could even work and stuff like this. And the approach we ended up doing is using the scratch area to save the register state. And then I'm opting to just like, then the goal is to return back to C++ after doing this in assembly, which is where the scheduler entry point, which is where we get to here. And then now that we're back in C++, and we also have the pointer to the kernel again, we can then just start using all the normal APIs and get the current task, copy in the state from the scratch area into the actual storage, and then really yield back to the scheduler. So that's an overview of like how scheduling works and how I've opted to implement it so far. And there's probably a lot of problems with it. Things will need to change later, but that is the current implementation. So with that, I need to get going. So I want to say thank you very much to everyone for this awesome stream. We got 50 people in the chat. This is way more than I've almost ever had, I think. I am super grateful for everyone in the chat right now. And yeah, I want to say thanks a lot. What about your setup? Okay, I need to go setup. And why did move not work? So honestly, I don't really know. There's like some difference between move and LEA in this case. And I think LEA, like move apparently did something unexpected. LEA is the idiomatic way to do computations involving like pointers and like offsets into structs and stuff like this. And so there is like some fine, I mean, we can ask the AI, why did move not work, but LEA did? There's like some subtle difference about that. Let's just see what it says. It's treated as a memory dereference. And so, yeah, it was like doing something like dereferencing G-kernel. So but it's pretty, it's like kind of subtle because, yeah, like, I don't know if it would be totally clear to me that gkernel is treated like a value as opposed to a pointer here. So yeah. Thank you very much, GSX Academy. Appreciate that a lot. My setup, you know, I have been getting a lot of requests about my setup. I'm just going to say, let's talk about it in the Discord. Yeah, so I got the Discord server. Feel free to join us over there if you want to chat some more. Thanks a lot, and I'm going to peace out. So yeah, I'll see you next week. Thanks a lot. Never give up. Have a great week, everyone. And I'll see you next week. We're going to keep it moving and debug that slowness thing. That was like super weird. Debug the slowness as the numbers got bigger, and keep working more on this schedule or whatever. So that's going to be it. All right.